Okay, picture this. You've got a massive global supply chain plan. We're talking thousands of rules all tangled together. But somewhere, deep inside, there's just one tiny broken rule that makes the entire thing impossible. It's a classic needle in a haystack problem, right? But what if you could search that haystack smarter, not harder? Today, we're diving into an algorithm that claims to do exactly that, and up to 10 times faster. Think about it. It's like you're a detective, and you've been handed a case with thousands of pieces of evidence, or in this case, constraints. They are all supposed to fit together perfectly, but they don't. Something's wrong. One rule contradicts another, and the whole system just grinds to a halt. Seriously, where would you even begin to look? This isn't just a fun little puzzle. For a lot of big industries, this is a very real and very expensive problem. So that brings us to this big idea, infeasibility. And trust me, this is not just a nightmare for coders. When a logistics company's master plan becomes infeasible, deliveries just stop. When a high-tech financial model becomes infeasible, trading strategies completely fall apart. We're not talking about minor glitches here. These can have billion-dollar consequences. So what's the tool that's building these incredibly complex plans in the first place? Well, it's usually something called linear programming. You can just think of it as this super powerful mathematical engine. Companies use it to find the absolute best possible plan, the lowest shipping cost or the highest possible profit, by juggling thousands of different rules all at once. It's basically the bedrock of modern optimization. Okay, so if linear programming is the engine, then infeasibility is what happens when that engine completely seizes up. It means the rules you fed into it are contradictory. The system is being asked to do something impossible. It's like having one rule that says this truck must leave New York at 9 a.m. and another rule that says that exact same truck must be in Boston at 9 a.m. See, the plan is just broken. That's our glitch. So the problem seems pretty clear. But how have people traditionally gone about finding these glitches? Well, for a long, long time, the approach has kind of been like fumbling around in a dark room. Let's take a look at the old and, let's be honest, really inefficient ways of doing this. For the longest time, there were really only two main strategies, and neither of them was what you'd call clever. First, you've got the sequential method. This one's the ultimate plotter. It just checks every single rule one by one, right from the top of the list to the bottom. Then there's the random method, which is basically like playing the lottery. You just pick rules at random and hope you get lucky. As you can probably guess, both of these are incredibly slow. And to see just how inefficient they are, let's look at a real example from the research paper. So we've got a system with 200 rules in it. But the glitch? It's caused by a tiny conflict between just 8 of them. So how long does it take the old methods to track it down? Get this, the sequential method had to check 197 rules before it finally stumbled on the conflict. 197, that's almost the entire set. Just think about all the wasted time and all that wasted computational power. Now, the random method did do a little better, mostly thanks to just dumb luck. It found the glitch after checking 42 rules. I mean, better, sure, but that's still a whole lot of guessing and a ton of wasted effort. There just had to be a smarter way to do this. And of course there is. This is where our new approach comes into play. It's called CEMA, which stands for Conflict Entropy Minimization Algorithm. This is our smarter detective. The huge difference here is that CEMA doesn't guess. It doesn't just plod through a list. It acts like a real detective. It looks at all the rules and calculates a conflict score for each one. That score basically tells it which rules are the most suspicious, the ones most likely to be part of the problem. And then it investigates those first. So how in the world does it come up with this conflict score? Well, it's a really clever mix of geometry and something called information theory, but we can break it down into 3 simple questions. First, directional opposition. Are any rules basically pointing in opposite directions, fighting each other? Second, geometric clustering. Are a whole bunch of rules all trying to control the same little area of the problem? And third, proximity. Is a rule getting really close to being violated by the current best guess? These are the clues that tell CEMA exactly where to look. And the process itself is just this simple, elegant loop. First, CEMA scores all the rules it hasn't checked yet. Second, it picks the single rule with the highest, most suspicious score and turns it on. Third, it checks, is the system broken now? If not, it just repeats that loop, getting smarter each and every time as it methodically closes in on the culprit. Okay, this all sounds great in theory, but does it actually work in practice? Let's get to the data. This is where things get really, really exciting. And here we go. This is the visual proof. CEMA is the blue bar, and the old methods are in red and orange. The difference is just stark. As the problems get more complex, that's moving to the right on the chart, you see the old methods really start to struggle. Their bars just skyrocket. But look at CEMA's blue bar. It stays incredibly low, consistently finding the glitch in way fewer steps. Let me put that another way. This shows how much work CEMA just avoids doing. On average, it skips checking over 85% of the rules. It's so good at figuring out which ones are suspicious that it can just ignore the vast majority of the innocent ones, which saves an enormous amount of time. And here is the absolute killer feature. CEMA doesn't just work, it scales. This chart shows its speed up compared to that old, slow, sequential method. See how that red trend line keeps going up as the problems get bigger? That means the more complex the system gets, the bigger CEMA's advantage becomes. And for real-world problems, that is exactly what you want to see. And this brings us to the headline number from the paper. In that test case with 200 rules, you remember the one where the sequential search took 197 steps? CEMA found the glitch in just 18 steps. 18. That's a speed up of almost 11 times. So a faster algorithm, what's the big deal? Why does something like this actually matter beyond the world of computer science? Well, ultimately, what CEMA really represents is more than just a clever piece of code. It's a fundamental shift in how we think about solving problems. Instead of just using brute force, throwing more and more computing power at something, it uses information to work smarter. It finds the answer not by checking everything, but by knowing exactly where to look. And this really gets you thinking about the bigger picture. CEMA solved its problem by learning to ask better questions about the data it already had. As our own systems in finance and logistics and science get unimaginably complex, it makes you wonder, maybe the biggest breakthroughs aren't going to come from bigger computers, but from better algorithms that just ask smarter questions. What other impossible problems are out there just waiting for the right question to be asked?